I will present the joint work of my colleagues Gustavo, Marcus, and myself on the topic of on-demand bias mitigation. And luckily, I can skip the title. So let's talk about a brief motivation. As we know, collaborative filtering algorithms rely on existing interactions between user and items, also called user-item interactions. But over the past years, research has shown that recommender systems potentially encode information about sensitive user attributes, such as gender, age, or country of origin, within the recommender system's latent space. As a consequence, this could lead to unequal treatment of different user groups or pose certain privacy concerns. So what is our answer to this? We propose to learn an input transformation that essentially alters the user-item interaction pattern and is applied to a pre-trained recommender system. So this means that we apply this transformation and essentially reduce the encoded information, in our case, about gender. So to highlight some benefits of our method, there's no need to retrain the full model again, as we apply it to a pre-trained recommender system. We can swap between biased and debiased model by choosing a parameter value. And as mentioned, we effectively reduce the encoded information about sensitive user attributes in the model's latent space. So how does this work? So our base model, which we also call the biased model, is based on the popular multi-VAE architecture, which means that for the model training, we use a loss term that consists of the reconstruction loss, basically trying to reconstruct the input vector, and the KL divergence as regularization term. The biased model will also be our baseline for task performance. So for the debiasing method of our choice, we are going for adversarial training, which means that we are adding an adversarial network on top of the latent space of our network and try to predict gender from that network. This means that the loss for the adversarial network is basically just a cross-entropy loss. And yeah, as said, try to predict the gender label. The combined model loss that we're using for the model training is then a combination of the recommendation loss that I mentioned earlier and the adversarial loss, which is parameterized by a scaling factor lambda. And yeah, the adversarial model that you see here will also be the baseline for our debiasing strength. So now to our model. As mentioned, we are applying this to a pre-trained recommender system, which means that we are freezing all of the weights of our recommender model and only update the weights for our input transformation network and for the adversarial network during training. But how does this input transformation look like? Essentially, we are using a simple multi-layer perceptron with only one hidden layer, which basically compresses the input space to a lower dimensional space and then projects it again to the original input space. Then we apply the sigmoid function, and then we binarize the output vector with a threshold function in order to achieve a binarized output vector, which reassembles user item interactions once again. So as the threshold function is non-differentiable, we need to approximate it, which is why we use the sigmoid function as a differential approximation. And then we basically take the gradients from the RecSys model and bypass our threshold function such that it is end-to-end trainable. Yeah, this whole method of binarization is inspired by the straight-through estimator, which is a popular vector quantization method. So after training, as mentioned, our model then provides the choice of two different modes. The first being you can basically feed the input vector directly into the encoder again, meaning you achieve the normal model. And the second mode takes the input vector, feeds it into the input transformation, and then continues propagating it, which essentially allows us to choose between a debiased model and the pre-trained biased model at inference time. So this means if we disable the input transformation at inference time, we go for the biased model and achieve optimal performance. But if we want to go for a debiased model, we enable the input transformation and essentially debias the input space with this. All right, talking about experiments. Our experiments, we conduct experiments on 3 different data sets of different scale. We have 4 different model variants, the first line being our biased model, the second line being an ablation study where we only use the input transformation but no adversarial training. The third line is the adversarial model, which is our baseline for debiasing strength. And the fourth line for each data set is our proposed method where we apply the transformation and the adversarial training. For task performance, we measure NDCG at 10. And for the debiasing strength, we are measuring balanced accuracy, which in the case of gender, where we have binary information, means that we have an optimal target of 0.5. So for task performance, to no surprise, I hope, the biased model achieves highest NDCG, meaning it's the best model. However, for debiasing strength, our model is able to significantly reduce the encoded information about gender within the model. And also in comparison to the adversarial baseline, we see that we are able to beat the adversarial baseline in terms of debiasing strength. but also stay competitive for task performance. In addition to those results, we conducted a short analysis on the influence of the scaling factor of the adversarial network. And the results here show that our method suggests that the balanced accuracy is lower across a range of different scaling factors, while also retaining a more stable NDCG across different parameter tuning sessions. All right, then for future work and limitations, we want to highlight that even though our method was only evaluated on the VAE architecture, in theory, this method is applicable to any neural architecture that expects a binary input and is able to be trained in an end-to-end fashion. And for future work, we would like to extend our work to the application of debiasing multiple attributes at once, and also potentially other bias types. We also would want to investigate explainability capabilities and also allow for a continuous transition between biased and debiased model, as we're currently only doing one or the other. And with this, thank you for your attention.
So you already said that in the outlook to future work that you only used the variational autoencoders. Was there particular motivation why you chose those? Are they particularly useful in this regard, or you had to start somewhere?
Yeah, I mean, like as you mentioned, at some point we have to start somewhere. It's also that we had a lot of experience with the multi-VAE architecture, and also like basically consulting recent work in the area of recommendations, especially for those data sets. The multi-VAE architecture was a very hot contender in terms of task performance as a baseline.
I was just wondering, what approach would we take to apply this technique to multi-label models? And yeah, do you have ideas as to like what would it just be like a multi-layer perception with like more hidden layers, or is there a different technique that would be applicable?
You mean the input transformation network?
Yes.
Yeah, okay. So for the question, what architecture we use for the input transformation network, if I got that correctly, it's just a simple feed-forward multi-layer perceptron. There's nothing fancy. It's just like going from one layer fully connected to a second layer fully connected. And that's basically it. And then obviously like the application of sigmoid and binarization.
So thank you for the talk. I wonder, since you have a data set from the news domain as well as from the music domain, whether you observed any differences in terms of the efficacy of your approach in these different domains, or whether this is just domain independent?
Yeah, so like as you mentioned, like we chose 3 different data sets from different domains because we wanted to show some sort of robustness across different domains, and they also, like all of them show a different sparsity, meaning that like there's a different amount of interactions from the complete item database. But in terms of training and evaluation of the recommender, I think I can quickly go through the experiments. Yeah, like the behavior was very similar, also in terms of different scaling factors. The only difference that we could highlight here is that for the news domain, we achieved a bit of a lower task performance, but we're not certain if this is just because of the data set itself, or if this is applicable because it's a different domain and more complex in that sense. Yeah. But across the training procedure, like we did not observe any significant differences.
Can we retrain useful information from gender in recommendations while eliminating discriminatory effects?
The question is if we can retain gender information while also eliminating discriminatory effects. So this, I'm afraid, goes a bit beyond the scope of our work. So I'm not quite sure how to answer this because we are focusing on eliminating gender information. In sequence that we can also eliminate discriminatory effects. I am not aware of a method now that basically keeps gender information but eliminates the same effect at the same time.